Okay, section 8.2a, testing the difference between means using small samples. Yesterday was large samples, right? Samples of size 30 or more. Today it's under 30. So as we've learned in this chapter in real life, it's often not practical to collect samples of size 30 or more from two different populations. However, if both populations have a normal distribution, you can still test the difference between their means. So in this section, you're going to learn how to use a t-test to test the difference between two population means using independent samples from each population, right? So conditions that need to be met, 3 of them. 1, samples must be randomly selected. 2, samples must be independent of each other. And 3, each population must have a normal distribution. For the two-sample t-test for difference between means, this is where it gets a little bit complicated. Okay. A two-sample t-test is used to test the difference between two population means, mean 1 and mean 2, when a sample is randomly selected from each population. Performing this test requires each population to be normally distributed, and the samples must be independent. The standardized test statistic that you would use is t is equal to excuse me, x bar 1 minus x bar 2 minus mu 1 minus mu 2. So, I'm sorry, what?
On the notes, is it like a hat?
So this right here is our two samples and the difference between them, right? So sample from population 1, or sample mean from population 1 minus the sample mean from population 2. So this is the difference in our sample means. Minus, and mu 1 minus mu 2, because when we do a hypothesis test on this, we assume that mu 1 and mu 2 are equal to each other, this portion is always 0, okay? Because if they're equal, 1 minus the other is 0. And then you divide by the standard error of the sampling distribution. Now this part right here is actually calculated using, this is kind of confusing, but this equation. Now, the difficult part of that is, this part is calculated using this if the variances are equal. If the variances are not equal, it's calculated using this. So there's a situation here where we have to decide, hey, are variances equal or are they not equal? And then we calculate the standard error depending upon whether they are or not. Here's the other part that's a little bit confusing. This is a huge equation in reality. Once you calculate this, it gets plugged in here. A lot going on, right? So if you actually look at this equation and you plugged this in here, like I just said, this is a really big calculation. So when variances are equal, there's a lot of work in order to just get the standard error that goes under here. Now, I'm not wondering if there isn't. I'd have to look into it. I've always just done the calculation or had students do the calculation, but there might be a calculator function that handles a lot of this for you, and we can look into that. So anyway, back to where I was started with this. The standard test statistic is calculated. It's t, and it's, you know, the difference in the sample means minus the difference in population means divided by the standard error. If variances are equal, if the population variances are equal, then the information in the two samples is combined to calculate what they call a pooled estimate of the standard deviation. And that's sigma hat, right? So standard deviation hat, or sample standard deviation. It's pooled. That's what they call pooled or combined. And you calculate it by taking the square root of n1 minus 1 times s1 squared plus n2 minus 1 times s2 squared all over n1 plus n2 minus 2. So this is a pooled standard deviation or estimate. You would then use that to calculate that standard error by plugging it in and multiplying by the square root of 1 over n1 plus 1 over n2. And in this case, a degree of freedom would be n1 plus n2 minus 2. Okay, and the reason why it's this instead of what we're usually used to, like n1 minus 1 or n2 minus 1, but we're combining both samples here. n1 plus n2 minus 2, we're subtracting 2 instead of 1 because there are two variables or two different populations that we're dealing with. If the variances are not equal, the calculation is much easier. If the population variances are not equal, then the standard error is simply the square root of s1 squared over n1 plus s2 squared over n2. Degrees of freedom are the smaller of either n1 minus 1 or n2 minus 1. So whichever one of these is smaller, that's what your degree of freedom is. Okay? And again, that's if your variances are not equal. So variances not equal, much easier. Variances are equal, bigger process. Okay? Let's take a look at how to do one. All right, guidelines. Using a two-sample t-test for the difference between means for small, independent. All right, so the guidelines are as follows. 1, state the claim. Identify your null and alternative hypotheses. So much like yesterday, our null a lot of times here is going to be that mu1 is equal to mu2, and that the alternative is that they are not equal. Okay, and you could state that as well by saying, you know, that mu1 minus mu2 is equal to 0, and that mu1 minus mu2 is not equal to 0. Okay. Step 2, specify your level of significance, alpha. Step 3, identify the degrees of freedom and determine which test. So this is the question is are variances equal or are they not? And then you have to identify the degrees of freedom. Okay, so when they say determine which test, that comes down to whether those variances are equal or not, and coming up with the standardized test statistic and having to figure out which standard error to calculate. Okay. Step 4, determine the critical values. So that's from table 5. You can find T naught. We've done that in the past. I don't think you're going to have a hard time with that. Step 5, draw a graph and find a standard error. Step 6, calculate the T. Right? So this is also going to be dependent upon whether the variances are equal or not. 6, calculate T. Then you would kind of place T on your graph and figure out whether you are going to reject or fail to reject. Step 8, interpret the decision in the context of the original claim. We've done all that many times before. Okay? So, find the critical values for the indicated alternative hypothesis, level of significance, and sample sizes N1 and N2. Assume the samples are independent, normal, and random, and that the population variances are A, equal, B, not equal. Okay? So, example 1. The alternative is that mean 1 is not equal to mean 2. Level of significance is 0.10. N is 11. N2 is 14. So let's, for A, our variances are equal. All right, going back here. Variances are equal. If my variances are equal, then my degrees of freedom are going to be n1 plus n2 minus 2, right? And in order to we have to come up with assume the samples are, find the critical values. So we're just finding the critical values. So based on this, we know it's a two-tailed test. We know our level of significance is 0.10. So if I were to draw a graph of this, I know that this is two-tailed because of my alternative hypothesis. And each tail is going to have 0.005 in it. And I can use the degree of freedom and that area in the tail to find my critical value T naught. So it's going to be negative and positive, right? So degrees of freedom in this case, 11 plus 14 minus 2 is 23. And what you can do is, you guys can use, right now you might want to try it in your calculator, inverse T, INVT, type in that area, 0.005, and I believe the degrees of freedom that it wants you to plug in would be 23. And tell me, does it give you negative 1.714? No? All right, so my bad. The area is not 0.005, but rather 0.05. And therefore, this would get us T naught is equal to, we would get the negative 1.714, and since it's two-tail, we know that the positive is also included. So now, what happens when we do this for variances that are not equal? Okay, so variances are not equal. Degree of freedom is the smaller of either n1 minus 1 or n2 minus 1. And then critical value. So the smaller would be n1 minus 1, right? 11 minus 1 is 10. Again, two-tail. Area of 0.05 in each tail. And if you do inverse T, you would get negative 1.812. And we would just get the other one, okay? Make sense? All right, example 2. The alternative is that mean 1 is greater than mean 2. Okay. Level of significance is 0.01, n1 is 12, n2 is 15. So if variances are equal for A, it would be n1 plus n2 minus 2, in which case we would get a degree of freedom of 25. Now, this is a right-tailed test, right? So if I drew a curve, it's going to be right tail. And that tail is going to have an area of 0.01. If I use inverse t and plug in 0.0, no, I'm sorry, I wouldn't plug in 0.01. What would I plug in? 0.99, right? I would have to plug in whatever this area is to the left. So inverse t, I'd plug in 0.99, degree of freedom of 25, and what I should get is a critical value of 2.485. Right? Then if variances are not equal, we would get a degree of freedom of n1 minus 1, which because it's the smaller sample size, so we'd get 11. Again, still its right tail. Area in the tail is 0.01. I get a critical value of positive 2.718. Let's try it out. Full-blown test. Example 3. The braking distances of 8 Volkswagen GTs, GTIs, and 10 Ford Focuses were tested when traveling at 60 miles per hour on dry pavement. The results are shown below. Can you conclude that there is a difference in the mean braking distances of the two types of cars? Use 0.01 as the level of significance. Assume the populations are normally distributed and the population variances are not equal. Okay. So population variances are not equal. Kind of sets the course for us a little bit. So here is the information given to us. GTI has an X bar 1, or a mean braking distance of 134 feet. Sample standard deviation of 6.9 feet and a sample size of 8. X bar 2, 143 feet for Ford Focus. S2 is 2.6 feet and a sample size N2 of 10. So we'd have to state the null and alternative hypotheses. Says, can you conclude that there is a difference in the mean braking time? So difference just means, can you conclude that there is a difference? Difference tells me that we're testing that this is not equal, right? Difference just means different. They're either equal or not equal. They're not saying, hey, can you conclude that one is greater than the other? So I know that I'm not using an inequality. It's just, can you conclude that there's a difference? So we would say the null is that they are equal, and our claim is that they are not equal. So this is a two-tailed test, and alpha is 0.01. And that means, I already wrote that, my bad. That means we have a two-tailed curve, and each tail contains alpha divided by 2, 0.05 in each one. Since variances are not equal, my degree of freedom is the smaller of n1 minus 1 or n2 minus 1. In this case, the smaller sample size is n1, 8. So my degree of freedom is 7. So I can find my critical values by saying inverse t and an area of 0.005, degree of freedom of 7, And in doing so, T naught is plus or minus 3.499, roughly 3.5, plus or minus 3.5. Now, since the variances are not equal, I can calculate my standard error for my standardized test statistic the easy way, right? This is the easy calculation for standard error. So standard error is S1 squared over N1 plus S2 squared over N2. Take the square root. In this case, I get 2.5743. And then I can use that to calculate my standardized test statistic T. Because this is my denominator for that calculation, right? So T is equal to x bar 1 minus x bar 2. In this case, 134 minus 143. Minus the difference in the mean populations, 0. Divided by the standard error, 2.5743, which gives me a standardized test statistic T, a standardized test statistic of negative 3.496. With that T statistic, I could plot it right in. This is really close. So my critical value is negative 3.499. My T statistic is negative 3.496. Super close. Super close. Nonetheless, it is in the fail to reject region. So we are going to fail to reject the null hypothesis. Since we're failing to reject the null hypothesis, we can say at a 1% level of significance. So again, we failed to reject the null, and the alternative was the claim. So there is not enough evidence to support the claim that the mean braking distances of the cars is different.